Hey, we're back with surface integrals. We're going to do a couple examples here, so let's get started. Remember, the main formula we're using here for a surface integral is we're integrating some function with respect to the surface on the surface. We find the shadow underneath that surface. We integrate the function, and then on that shadow region, that area stretches by this much to turn into the surface area. So that's the main question. The first one says, find the surface area of the portion of the paraboloid z equals x squared plus y squared below z equals 8. All right, so the first thing is they're asking us for surface area, so we want the integral on the surface of the one function ds. That will give us surface area. So the function f in this problem is just 1 because they're asking for surface area. That's going to turn into a double integral over the region below that shadow for 1 times that stretch factor, which is going to be, remember, if the surface was coming from some function g, it would be gx squared plus gy squared plus 1, and then dA. Okay, so now we got to figure out, well, what is g? Well, g is equal to this 2x squared plus 2y squared function. So gx is just 4x and gy is just 4y, just taking those partial derivatives. So this gives us the integral over the region of 1, which we can just stop writing because 1 is 1, square root of 4x squared plus 4y squared plus 1 dA. Alrighty. And then we got to figure out, what is that region R? Well, it says it's the part of this surface that's below z equals 8. So if I remember correctly, this looks kind of like a paraboloid. There's z equals 8 right there. So if I kind of take the shadow underneath and of it, I think what we would get is a circle down here in the xy plane. And if I set 8 equal to 2x squared plus 2y squared, that's 4 equals x squared plus y squared. That's just a circle of radius 2 down in the xy plane. All right. So what you could do is turn this into a double integral in rectangular coordinates. Turn this into dx dy. But then the bounds would be kind of messy, and because it's a circle, I'm wondering if I'll just turn this into polar coordinates. I think that'll be easier. So in polar coordinates, a circle of radius 2 is just r equals 0 to 2, theta equals 0 to 2 pi. This is really, what, 16x squared plus 16y squared, so that's just 16r squared, so the square root of 16 r squared plus 1 inside, and then dA is going to become r dr d theta because we used polar coordinates. So in fact, I think this integral would be very difficult if we didn't use polar coordinates. But now that it's set up, it's just a calculus problem. So this is the surface integral problem, right? You have a surface integral, you write down the formula, you find your function that's telling you what the surface is, that gives you those and those, and then the region gives you the shadow underneath it, that tells you what r is, and then in this case, r was a circle, so I ended up switching it into polar coordinates to actually do the integral, but r could be a rectangle in general. Okay, so let's see if we can work out this integral now. Integral 0 to 2 pi, integral, let's do a U-Substitution. So u is equal to 16r squared plus 1, du is then 32r dr. And so I don't have a 32, do I? So let me put in a 32, and then I'll have to divide by 32. So I'm going to have 1 over 32 here, and then I'll end up with the square root of u du d theta. And then what do my u's turn in here? U was 0, or r was 0, so that's 0 plus 1 is 1. And then r was 2, 2 squared is 4, 4 times 16 is 64, plus 1 is 65. Okay, So now I've done a U-substitution, so now we can actually do the calculus here. So I've got 1 over 32 on the outside. This is going to be 2/3 u to the 3/2. That's the antiderivative of root u evaluated from 1 to 65 d theta. And then we're going to have, well, we'll have 2/3 of 65 to the 3/2 minus 1 to the 3/2, which is 1 d theta. And so now we're going to have, let's see, 2/3 times 1 over 32 would give 16 times 3, 1 over 48. And then 65 to the 3/2 minus 1 theta evaluated from 0 to 2 pi. And so that's going to give me pi. 2 pi over 48 would be pi over 24. 65 root 3/2 minus 1. And that's the answer for that one. All right, let's do another one now. A thin metal sheet, or so-called a lamina, is in the shape of the section of a cone, 6 minus x squared plus y squared square rooted, which lies between z equals 2 and z equals 5. The mass density of the sheet is delta xyz equals root x squared plus y squared. Find the object's mass. Okay, that's interesting. So we've got some cone, kind of looks like that part of a cone, except it only lies between z equals 2 and 5, so we've kind of cut it off between 2 and 5. So what you really have is maybe what you'd call the frustum of a cone, I guess, I think is the term for it. And what happens is this surface has different densities at different places, so that's the density. Okay? So what they want us to do then is integrate over the surface the density times surface. That'll give us the mass. Okay, so the mass comes from integrating the density along the surface. And what we learned is to do that, we're going to integrate over the region below it, the density function, which in this case is square root of x squared plus y squared, times the square root of gx squared plus gy squared plus 1 here. And what is that? Well, g, and then that'll be dA. So that g function is 6 minus root x squared plus y squared. That's the cone, right? The cone is giving you the surface. If you take gx, you're going to get, what, negative 2x over 2 root x squared plus y squared. And gy would be negative 2y over 2 root x squared plus y squared. So when you square that, you're going to get, the 2's will cancel, you're going to get x squared over x squared plus y squared, and then you'll get y squared over x squared plus y squared, and then you'll get plus 1. So this is your f that we're integrating. This is the stretch factor times dA gives you ds, right? That's how this works out. And so now it looks like we've got a little bit of algebra to do. Integrate over the region, root x squared plus y squared, common denominator x squared plus y squared over x squared plus y squared plus 1 dA. Well, x squared plus y squared over x squared plus y squared, that's just 1, and 1 plus 1 is 2. So this is really just root 2 integrating over the region x squared plus y squared. And I think what we're going to do is, again, switch this to polar coordinates, because that's just going to be root r squared, and then we can go r dr d theta. This is a nice polar coordinates problem again. Theta is going to be 0 to 2 pi, because we've got, when we cast our shadow down here, we're going to get what looks like a annular region in the xy plane. Okay, and so all we need to do is figure out what the radiuses of the radii of these two circles, because they're going to go 0 to 2 pi all the way around. Okay, and so to do that, we're going to, so let's work that out. So we've got 6 minus, well, that's r. 6 minus r is equal to the z coordinate. There's z right there, and z is 2 and 5. So if that equals 2, then you're getting r equals 4. And if 6 minus r equals 5, then you're getting 1 is equal to r. Okay, so r goes from 1 to 4. All right, so now we can just do this double integral here. So we've got root 2 integral from 0 to 2 pi for the thetas. Okay, root r squared is r. R times r is r squared, so that's going to be r cubed over 3 when we take the antiderivative, evaluated from 1 to 4, d theta. Root 2, 0 to 2 pi. 4 times 4 is 16, times 4 is 64. So we got 64 thirds minus 1/3 d theta. And then that gives us root 2, 63 thirds. And 63 thirds is better known as 21. And then theta from 0 to 2 pi. So that's going to give us 42 pi root 2 as the mass of that object. Okay, so there's two nice examples of a surface integral where you know the function. And the function could be 1 giving you surface area, or the function could be a density when you get the mass, or it could be some other quantity, and then I guess you'd get something else. So hopefully you find that helpful, and we'll see you in the next video.